Have you ever wondered how people survive in arid desert environments, where water seems almost non-existent? Despite the harsh conditions, humans have developed remarkable strategies to locate and utilize water sources in these regions. Even in the driest deserts, water can be present in various hidden forms. It may exist underground, stored in aquifers, or collected in natural depressions that capture rainwater. Some desert plants and certain types of soil can also retain moisture, which can be extracted with specialized techniques. Understanding the distribution and availability of water in desert ecosystems is crucial, not only for survival but also for scientific research and sustainable resource management. By studying these strategies, we gain insight into both human ingenuity and the complex hydrological systems of arid landscapes. Even in regions with flowing surface water, water scarcity can still occur. Interestingly, these streams and rivers often contribute to the replenishment of water stored in deeper layers of soil and rock formations. This underground storage plays a critical role in sustaining ecosystems and human communities during dry periods. Water stored underground in permeable rock or sedimentary layers is known as an aquifer. Aquifers act as natural reservoirs, slowly releasing water over time and providing a vital source for wells and springs, particularly in arid and semi-arid regions. Permeable soil refers to soil that allows water to pass through it easily due to its structure and composition. Such soils typically have larger particles, like sand or gravel, which create interconnected spaces or pores. These pores enable water to infiltrate and move downward, eventually reaching underground layers such as aquifers. Permeable soil refers to soil that allows water to pass through it easily due to its structure and composition. Such soils typically have larger particles, like sand or gravel, which create interconnected spaces or pores. These pores enable water to infiltrate and move downward, eventually reaching underground layers such as aquifers. In this illustration, it is clearly visible that the grains or particles are spaced apart, creating open spaces between them. These gaps allow water to infiltrate and move through the material, as illustrated on the right side of the diagram. This demonstrates how well-connected pore spaces facilitate the flow and storage of water within the soil or rock. Rock or soil can also be non-permeable and non-porous, as shown here. In this case, the particles are so tightly compacted that there are virtually no spaces between them. As a result, water cannot seep in or move through the material. This lack of permeability means that water remains on the surface or is forced to flow laterally rather than infiltrating downward. Consequently, such layers can prevent groundwater recharge and may lead to surface runoff, erosion, or even the formation of temporary water bodies above these impermeable layers. In this experiment, water is poured onto two types of rock, sandstone and granite. Observe carefully what happens. The water poured onto the sandstone slowly seeps into the rock. This indicates that sandstone is permeable. Its porous structure allows water to pass through the interconnected spaces between the grains. In contrast, the water on the granite remains on the surface and does not penetrate. Granite is non-permeable because its mineral crystals are tightly interlocked, leaving no connected pore spaces for water to enter. From this simple observation, we can conclude that sandstone allows water infiltration, while granite acts as a barrier to water movement. When we watch the video again, it becomes clear that the water poured onto the sandstone is absorbed into the rock, while on the granite, the water flows off the surface. This difference can be explained by the internal structure of the two rocks. Sandstone is composed of small mineral grains that are loosely packed, leaving open spaces, called pores, between them. These interconnected pores allow water to infiltrate and move through the rock, making it permeable. Granite, on the other hand, is made up of tightly interlocking crystals formed deep within the earth. Because there are no connected pore spaces, water cannot enter or move through it. As a result, granite is impermeable, causing water to run off its surface instead of soaking in. However, even granite can contain small amounts of water. This water is not newly absorbed from the surface but is often trapped within microscopic fractures or mineral crystals that formed when the rock solidified millions of years ago. Such water is sometimes called connate water or fossil water, as it has been enclosed in the rock since its geological formation. These tiny inclusions show that even apparently solid rocks can preserve a record of water from the Earth's deep past. An unconfined aquifer, also called a water table aquifer, is a layer of permeable rock, sand, or gravel that holds and transmits groundwater. It is directly open to the atmosphere through the porous materials above it, so the water level in wells equals the water table. The structure can be separated in three boundaries. Top boundary, water table, the surface where the ground is saturated. The structure can be separated in three boundaries. Top boundary, water table, the surface where the ground is saturated. Above, permeable soil and rock allow infiltration of rainwater and surface water. Have you ever wondered how water can be stored deep underground, protected by layers of rock and sediment? Welcome to the world of confined aquifers, a vital part of our planet's hidden water system. A confined aquifer is a water-bearing layer of permeable rock or sediment, sandwiched between two impermeable layers. These impermeable layers, often clay or dense rock, act like seals, trapping water under pressure. Water enters the aquifer through a recharge area where the permeable layer is exposed at the surface. Rainfall and surface water seep down, replenishing the aquifer over time. When a well is drilled into a confined aquifer, the pressure built up between the impermeable layers can cause water to rise in the well, sometimes even reaching the surface without pumping. This is known as an artesian well. Sometimes it even reaches the surface without pumping. This is known as an artesian well. An artesian well is a type of well that taps into a confined aquifer, a groundwater reservoir trapped between two impermeable layers, such as clay or rock. Because the water in this aquifer is under natural pressure, it can rise up the well without the need for pumping. Confined aquifers are crucial for supplying clean water to communities, especially in regions where surface water is scarce. Their natural protection makes them less vulnerable to contamination, but also harder to recharge. Understanding confined aquifers helps us manage groundwater sustainably and protect one of Earth's most precious resources. Thanks for watching.